squared, and that of course was cosine of theta. So there's a lot going on, a lot of digits that you have to plug in. Yeah, it's a nuisance, but you've got to do it, okay? And then on this guy, of course, this was just K, Q12, Q5 over root 2 of R squared. Y'all know where that root 2 of R is coming in? That's this distance, right? There's a right triangle. Since these are both R, this is root 2R, correct? And that was then sine theta. Okay? Now, once you found these quantities, can anybody tell me what the net force on the X came out to be and what the net force on the Y came out to be? Nobody finished this? What? They turned it in. I wonder if everybody did it. Number 9, here we are. Okay, you did. Oh, good. I'm using Mr. Peasley's here. So he found the net force on the X to be 20.9 newtons, and he found the net force on the Y to be 23.5 newtons. So if we go back to that drawing, what he did is he found the difference between these, which would still be pointing this way, I think. It ended up coming out positive. So it's actually pointing that way, and then he found this quantity. And those in newtons came out to be this and this, okay? So then what we have on that charge, that 5 microcoulomb charge, is we've got a net force on the Y pointing up, and a net force on the X pointing this way. So to find the magnitude of the net force, now that we've found the X and Y component, what can we do? Pythagorean theorem, right? To find the overall net force. So in other words, net force would equal the square root of the net force of the X squared plus the net force of the Y squared. Correct? Yeah. Okay, when I start doing problems though today, I need everybody writing everything down, okay? It's gonna start getting really, really hectic, okay? So, yeah, you've gotta really follow along here. I'm just trying to finish this problem because these were really easy. Okay. Anyhow, you end up getting a net force of about 31.5 newtons using Pythagorean theorem there. Then you also have to find the direction. So what's a way that I could define this direction? What's a standard place to give all angles from? Positive x, positive x. So we're going to find what that angle theta is, okay? So what can I do to find what that angle theta is? Yeah, you can use sine, cosine, or tangent theta. Tangent theta is typically what you do, like we didn't even have to find this to find the angle. We could just use tangent, which is the adjacent and opposite, and use that to find theta. We know that tangent theta is equal to the opposite side, opposite over adjacent, right? So the opposite side of this triangle is going to actually be the net force on the Y divided by the net force on the X. And then to solve for theta, we inverse tangent net force on the Y over net force on the X. And that gives us the angle from the positive x-axis, right? Yes? Okay. So, okay. Let's take a look at this again. We'll do a lot of examples out of this. So we have that. Let's go over to number 132, electric fields. And let's draw a few of these out. So if everybody can look at number 12, on physics. So every day we're going to be using this and our notepad, okay? So every day just automatically get those out. So number 12, it says use at least 8 field lines for each diagram, okay? So we want to draw the field line diagram. So let's just say 4 lines coming out of each charge. How about that? Start with 4 lines coming out of each charge. So let's see, what would the E field diagram look like on A here? Or positive Q, positive Q. What do we got going on here?
They're going out.
Yeah, they're going to be diverging. They're going to be diverging. So if you were to draw 4 lines for each one, these would diverge away. Right? What would you expect the E field to be at exactly midway between these 2 points? 0, right? It would be a 0 E field exactly midway between these 2 points. Okay? What about the B? How would B look? Who would have more? What has changed here?
The charge.
This charge is 2Q now, right? So how many lines do I need coming out of him?
Twice as many.
I need twice as many coming out, right? Now, let me ask you this. At a point, right in the middle, what would the E field be now? Would the E field still be 0? Absolutely not, it wouldn't. Because this guy has a greater magnitude E field than the other one, right? So give me a prediction. If I were to draw an arrow for what the E field looks like right there at the middle, what more or less would it look like? Where would it be pointing? Pointing that way. There would be an E field pointing that way. Yes?
Was there another point out saying mass would be off?
Right, we could find a place where it would be 0, but that place is going to be logically closer to him now. And how could we find that? We could find that using the exact thing we did with force, but with E field, because E field is KQ over R squared instead of KQQ over R squared. And we're going to do that exact same thing now. We're now going to just find it in terms of E field. It's the same as doing it with force. You can do it as vectors. So, what about C? What about C? How's that going to look? We got is it positive and negative?
Yes.
Okay. So we'll do 4 lines for each to the same charge. So, how would I draw this guy?
You should have not made that one a straight line then. You should have made like an even smaller ellipse.
No, I'm not too worried about it. Whatever. Now you got to remember, a lot of times students will think that, oh, well, the E field line's got to originate from somewhere. So a lot of times students with negative charges, they're like, but those lines are coming from another positive, right? No, that's not actually how it works. The negative produces the lines itself. The whole direction thing is just a way to differentiate that they are different sign charges, okay? A negative all by itself produces field lines. We draw them as pointing towards it, okay? It's not like only positives produce them. That's just the notation that we use, all right? So now the question would be, what's the E field right here going to look like? Where's it going to be pointing? And who's that E field going to be caused by? Let's say this guy produces an E field E, and let's say this guy produces an E field E. What's going to be the magnitude of that E field there? Why is the magnitude of that E field right there going to be 2E? Because they're producing E fields that point in the same direction, in this case. Whereas in the other one, we had these diverging E fields because they were pointing in opposite directions vectorally. Now they point in the same direction. Y'all kind of understand that idea?
Yeah.
Okay, and this is just so when you're doing a more complex problem, you get the idea of the orientation of where the E field would go. All right, so you get the direction of the E field there. Obviously in E, it's going to look just like A, except they're going to be pointing towards, right? Okay, let's just do D really quick. Is that what it is?
Yes.
All right, let's do 4 lines for these, and we'll do how many for him? We use the 8. Okay, this is kind of weird. So I can definitely say that. Okay. From that, I'm gonna do this and this. I feel safe doing that. Maybe doing that. All right.
It'll still work, because now I'll have it, just do an inner one now, the inside. With the pluses, draw arrows inside.
Yeah, you're right. Like this.
Yeah, and that's it. That's,
Yeah, I'd agree. Now, in this case, what would be the E field right here? What do y'all think? A prediction?
towards the negative.
Would we have an E field right there? Well, I don't know, because this guy produces an
No.
E field that pulls in.
Yeah,
But he produces an E field that goes this way.
Would not the other way, not between Q and Q.
I would say the E field probably looks like that right there. Yeah. And then what about right here? It'd just be longer, right? Because the density is getting greater. Y'all kind of see what I'm doing here?
yeah.
What about over here? What would it look like? Right. What about right in here? You'll see what I'm doing here? These are kind of like little test points of what would fundamentally that E field look like as a vector at that exact point. And the way that we do that is that we treat these points as if they were little positive charges. Where would the electric field force them? There's not actually a charge there, but I'm saying if you were to put a tiny little positive charge, where would the electric field force it? Well, right, where is it going to be attracted? Towards that negative. So that's that direction of the E field in that moment, right? Because that's where that charge would be pulled if there was a charge there. And that idea is called the test charge, test point. We just imagine it, well, how would the E field line be pointing at that place, okay? So let's turn the page to homework numbers 133 on the homework assignment, and take a look at this.
Okay.
So,
Yeah, well,
133, the next page. Okay. So yesterday, what is the E field expression for a point charge? We derived it. Does anybody know what that is? KQ over R squared, right? What does that look very familiar to?